For Chapter 2.1, we are covering mathematical writing. This includes disproving statements by example, writing simple proofs as to whether things are even, odd, or divisible by some number, and tracing proofs. Disproving statements can be easier than actually proving them. To disprove a statement, we only need to find one example where the statement is false. And remember with implications that for something to be false, the hypothesis must be true, and the conclusion must be false. So as an example statement, let's say that someone said if some number is even, then some number plus 1 is also even. And we know already that this is false, but to show that this is definitely false, to disprove it, we'd have to come up with, let's just say P, then Q. We have to come up with some valid P, so some even number is only going to be valid here. It's not going to work if we have 3 or 5. So we have to choose some even number to play by the rules. And then we have to show that the result is false. So with each of these, none of these end up being an even number. So we can disprove just by example that this statement is incorrect or invalid or false. And remember, the negation of P then Q isn't an implication, it's P and not Q. So we have a true hypothesis, but our conclusion ended up being false. So false. So proving a statement requires more than just plugging in numbers to see what works out, because we would have to check the entire domain, and usually this is infinite. But at least for disproving statements, we can plug in values and show an example where the statement is invalid. So for example, if we have a statement saying, for every integer, if n is odd, then n squared plus 4 is a prime number, we can plug in various values. Now, it might be true for 3 or 5, but once we get to 9, we can see that this is 81 plus 4, which ends up being 85, and 85 is divisible by 5 and 17, so we've proven the statement false. So in order to do our simple proofs, we need to look at these definitions. First is if something is divisible by 4, and we can extend this to other numbers as well. Say we have an integer n, and it's claimed that n is divisible by 4. Well, in a proof, instead of writing n, we might write 4m, where m is some other integer, showing that n is equal to 4 times m. When we need to write a number n as an even number in a proof, we'd then instead swap it out with something like 2k, because 2 times some integer will always be even. And for odd numbers, we'd swap them out with something like 2l plus 1, because an even number, which would be like 2k, plus 1 will be something odd. So to restate that, using the definitions of even, odd, and divisible by some number, we prove statements by subbing out simple variables like x with statements like 2k plus 1 for odd, 2l for even, or 4m for divisible by 4. So for example, if we need to show that 10 is even by writing it as a proof, we need to show that 10 is equal to 2 times some number. So if we just factor it down, 2 times 5 is equal to 10, so we can indeed show that it is even. And for the statement, the result of summing any odd integer with any even integer is an odd integer. We'll have to think of these in terms of 2k plus 1 and 2l to represent our even and odd integers. And we need to recognize that the outcome should be in some form of 2n plus 1, where n is probably something like k and l combined. So we start by changing the concept of odd plus even into a mathematical statement. So 2k plus 1 plus 2l. Then we can get rid of these parentheses and try to combine them. And if we factor out the like term of 2, we can see that k plus l, adding two integers together, results in a third integer. So 2 times some integer plus 1 is an odd number. Finally, we'll also be tracing proofs. This means taking a proof and plugging in some numbers just to test it out. This is similar to how we were trying to disprove statements, but we're not doing this with the intent to disprove, only to familiarize ourselves with the proof. So for example, if we have the proof that for all integers where n is greater than 4, if n is a perfect square, then n minus 1 is not a prime number. So we can just plug in a few different numbers and see what the outcomes are and make sure that the statement is true. So let's say we have the statement, if n is even, then 3n is even. So instead of representing n in a proof, we'll say n is equal to 2 times some number. And our result is going to be 3n is equal to 2 times some other number, but we'll have to run through the proof to prove this. So let's say we have if 2k is an even number, and we have 3k, if we multiplied this out, it'd be 6k, which we know that's even. But we just need to rewrite it in this form. We don't need to multiply this out. So since we have 3 times 2, we could also write that as 2 times 3. So we can end up getting 3k. And so this is how we would prove it. It is 2 times some other number, and it doesn't matter what this is, because we have our 2 here. And here we have, if n is odd, then n cubed minus n is divisible by 4. So we'll have two different ways of representing this. Let's say n is 2k plus 1, and we want the result to be 4 times some number. So we'll be computing this as n in order to find out if we have 4 times some number, some L. So we just start off by saying n cubed minus n, so 2k plus 1 cubed minus 2k plus 1. So if we end up multiplying this out, we'll get 2k plus 1, 2k plus 1, 2k plus 1, and then minus 2k plus 1. Now, if we did the FOIL on all of this stuff, we should end up with something like 8k cubed plus 12k squared plus 6k plus 1 for this whole part, and then let's distribute this negative sign. So then we'd have minus 2k minus 1. So if we combine like terms, then we'll end up getting 8k cubed plus 12k squared plus 4k, because plus 1 minus 1 and plus 6 minus 2. Okay, so now these have a common number of 4. We can say 4, just factoring that out. This will end up being 2k cubed plus 3k squared plus a single k. And now we've gotten it to the form where it's 4 times some number, and so it is divisible by 4.